In this problem, we are being asked to predict products of that. So again, we need to be considering is multiple substituents, what type of substituents we have, activating, deactivating, and how they direct an electrophilic aromatic substitution, which is a reaction that you're doing, a bromination. So analyzing the first molecule here, you have this group is activating VOH. You can act as electron donor by resonance. So I'm going to write activating. Let's say here, this group is deactivating the sulfonic group. And here you need to remember all that. So a couple of things that we need to remember when we're doing problems. One is what groups are activating, deactivating, and how they orient. The other is reagents. What is the electrophile that you're installing? So reagent here means this is a bromination, you're installing a bromine. And now we're analyzing the type of substituents. Here, this is an area is similar to another problem that we did before. So activating, deactivating. When this is the case, the group that is going to determine where the next substitution is going to happen is the activating group. So DOH. Next, activating is this group, activators, direct, ortho, para. So we need to identify those positions. So ortho, so the hydroxy, ortho to the hydroxy, para is occupied. So what is our product, which is our goal here, determining products. So the substitution, the bromine is going to enter ortho to the OH. That's my sulfonic acid. So what was the analysis then? Two substituents, activating, deactivating. The substitution is going to be determined by the activating group and is ortho-para directing. So now the molecule below, we're doing the same type of reaction. So we're installing a bromine, but where? Now, notice that these are two esters in this molecule, but what is attached to the ring is different. In the molecule, the substituent under here, what is directly attached to the ring is the oxygen. So you can think of doing resonance structure, donating electrons toward the ring. You can also do so toward the carbonyl. But this group, because it can donate electrons over to the ring, is activating. So remember, that's the first step. We need to determine what each group is. So activating, and as all activators, it is ortho-para directing. Now let's look at the other group. It is another ester, but it turns out that now the carbonyl is what is directly attached to the ring, and this is electron withdrawing. So notice, depending on what is attached to the ring, the ester group is going to function here as activating, attached by the O, and here by the carbonyl. So this is deactivating, and it is meta-directing. The only exception of deactivating group that is ortho-para is the halide. So that one big exception that we need to remember. Everything else is going to be meta-directing. So now that we have established that there are two ester groups, but this is activating because it has the O directly attached to the ring, and this is the opposite. So activating, deactivating, the activating group is going to determine where is the substitution going to occur. So ortho-para, so ortho-para. And here we have the problem that this position in the center, we're not going to introduce any substituent there because of a steric hindrance. It is in between two groups. Now I have two products. One is going to be here and one is going to be, so ortho to the other group. So let's do the two products. Again, the one with the substitution between two groups is not going to happen. So I'm going to have the ester that is very light. So I'm doing my substituents as I had it at the beginning. One is going to have the bromine here, and the other is going to have, let's change that right there where the other arrow is. So bromine here. So again, here we must remember what is that is attached to the ring, because it might be confusing. Is ester group, but remember that when you have the oxygen directly attached to the ring, you can do resonance and donate electrons to the ring. That's why this is activating and this is deactivating. And here we need to pay attention to other cases similar to that, which is amides. So if you had, say, this, and that's an amide, right? That's benzamide. The carbonyl is directly attached to the ring, so this is deactivating. And now if I do another amide, let's do another, and I put the N here, and say, so that's N-phenyl acetamide. And so now, directly attached to the ring, you have the nitrogen with the lone pair. You can delocalize toward the carbonyl, but also to the aromatic ring. So this group, as is activating. So I'm going to do the arrow to remind you guys that you can do resonance, and it acts as electron donor. So this group is activating, and if the amide is drawn the other way, with the carbonyl attached, is deactivating. So similar to that. Carboxylic acids also, if they are attached, the carbonyl directly, is deactivating.